Hi everyone, this is BB Singh and today I am going to discuss a problem of design of knuckle joint. So do subscribe for the latest videos of machine design. So here we have to design a knuckle joint to transmit the pull of 150 kN. The permissible stresses are 75 megapascal in tension, 60 megapascal in shear and 150 megapascal in compression respectively. So let us see what we have in the given. We have the load which is applied on the axial pull type of load of magnitude 150 into 10 raised to 3 Newton. We have the permissible stress in tension 75 Newton per mm square. We have the permissible stress in shear 60 Newton per mm square, and we have the permissible stress in compression which is 150 Newton per mm square. So here I have shown the figure of knuckle joint. Okay, so here first we are going to calculate the diameter of rod A and rod B. As we know that I have explained during the design procedure, after the application of force P, there is a possibility of failure of rod in tension. So let us calculate the induced tensile stress by using the formula tau is equals to sigma T is equals to P by A. So here we have the value of sigma T, which is the permissible or allowable stress in tension, which is 75 Newton per mm square. We have the value of P. We can calculate the area. Okay, so area under tension for the rod A and rod B is pi by 4 d square. So I am going to rewrite this equation in terms of d. It will be d is equals to root of 4p divided by pi into sigma t. So by using this formula, I am going to calculate the diameter of rod A and rod B. So let us put the value of P, which is 150 into 10 raised to 3. Sigma T is 75 Newton per mm square. So let us calculate the diameter of rod. So as per the calculation, the diameter of rod is 50.46. So I have rounded it to the next digit of 51 mm. So here we have calculated the diameter of rod A and rod B. So by using this diameter, we can calculate the remaining parameters which are related with the rod. So the next is the enlarged diameter D1. Okay, so here you can see that this is the enlarged diameter. So by using empirical relation, D1 is equals to 1.1 into diameter of rod. So here we have calculated diameter of rod is 51 mm and the calculated diameter of enlarged diameter of rod is 56.1 mm. So I am going to round it to the next digit of 57 mm. So here by using the empirical relation, we have calculated the enlarged diameter D1, which is 57 mm. Next I am going to calculate the thickness of eye. Okay, thickness of single eye. Okay, this is the thickness of single eye, which is actually represented by B, and as per the empirical relation, B is 1.25 times the diameter of rod. Okay, so B is equals to 1.25 D. So here in the problem we have calculated the diameter, and diameter is 51 mm. For the diameter of 51 mm, the thickness of eye will be 64 mm. Actually it is, as per the calculation, 63.75. So I have rounded to the next digit of 64 mm. Okay, so next is thickness of fork. So here you can see that thickness of fork is represented by A, and thickness of fork is 0.75 times the thickness of the diameter of rod. Okay, so here I have calculated the thickness of fork A, which is 38.25. Again I have rounded it to the next digit of 39 mm. Okay, so here the thickness of fork is 39 mm. So these are the some values which I have calculated by using empirical relation. So these parameters like enlarged diameter, enlarged diameters of rods, thickness of eye and thickness of fork are totally depend on the diameter of rod, that is capital D. Next is we have to design the pin. Okay, so during the you can see the video of design of knuckle joint. In that video I have explained the design of pin. There is a possibility of failure of pin in various manners. So first is the pin can fail in shear, second is the pin can fail in bending, and third is the pin there is a possibility of failure of pin in crushing. So let us discuss one by one. So first I am going to consider that the pin is going to fail in shear. So here I have shown the free body diagram. So after the application of force force on the eye and fork, here you can see that there is a possibility of failure of pin along this plane and along this plane. So here double shear failure is there, you can see that, and the shear applied force P, it will act over the area, it will act tangent to area. So the shear stress tau will be equals to P divided by 2a. Here the digit 2 represents there is a double shear, that is why I have multiplied the area by 2. Okay, so here we have to consider the area of pin. So area of pin is pi by 4 d square, where small d is the diameter of pin. So once I'm going to put once you will calculate the area, you have to just put this formula of area of pin, area of cross section of pin in this equation. So the equation will be tau is equals to 2p divided by pi d square. Okay, so after the simplification we can convert this equation in terms of small d, that is diameter of pin. D is equals to root of 2p divided by pi into tau. Okay, by using this equation we can calculate the diameter of pin in shear. Okay, so let us put the value of p, which is something 150 into 10 raised to 3 Newton. Okay, and we have the value of tau, permissible shear stress. So put the value of p and tau in the equation. Okay, so after putting the value of p and tau in this given equation, I found that the diameter of p d is 39.89. I have rounded to the next digit 40 mm. So here I am going to select the diameter of pin as a 40 mm according to the shear failure of pin. Next, I am going to calculate the diameter of pin in bending, and I am going to compare the diameter of pin in shear and the diameter of pin in bending, and I will select the which one is having larger value. Okay, next is the failure of pin in bending. So here I have shown the free body diagram again. Okay, here you can see that the portion which is contained inside the eye, it will be subjected to uniformly distributed load, and the portion which is contained inside the fork, it will be subjected to uniformly varying load. So here during the design procedure we have derived one formula of bending stress sigma b for the pin. Sigma b is equals to 16p divided by pi d cube multiplied by b by 4 plus a by 3. Already we have calculated the dimensions of I and fork, that is b and a. We have the value of p. We have the value of sigma b. Actually in the problem sigma b is not given, but we can assume that the bending stress is equivalent to tensile stress, and we can take the value of tensile stress as a bending stress, that is permissible. The value of permissible tensile stress will be equal to permissible bending stress. Okay, so by I'm going to convert this equation in terms of d to calculate the diameter of pin. So let us rewrite this equation. So d is equals to cube root of 16p divided by pi into sigma b multiplied by b by 4 plus a by 3. Okay, so let us put the value of b, value of a, and value of p and value of sigma b in this equation, so that we can calculate the diameter of pin in bending. So in this problem bending stress is not given, so we need to assume that the permissible bending stress sigma b is equal to permissible tensile stress sigma t, and the value of permissible tensile stress is 75 Newton per mm square. So let us calculate the diameter d. So here you can see that after the simplification I found that the diameter of pin d is 66.59. I have rounded to the next digit of 67 mm. So in the previous slide I have calculated the diameter of pin in shear, which was 40 mm as per the calculation, and diameter of pin in bending it is 67 mm. So let us select the maximum one. So the maximum value is 67 mm. So the diameter of knuckle pin, I am going to select the diameter of knuckle pin as a 67 mm. So by using this diameter of pin, next is I am going to calculate the various dimensions of eye and fork which are depend on the diameter of pin, as the diameter of pin is the inside diameter of eye and fork also. So let us calculate here we have calculated the diameter of pin as 67 mm. Let us calculate the outer diameter of eye. As we know that the outer diameter of eye is having circular shape, it is having the diameter do. It is the twice to the inner diameter of eye, or it is twice to the diameter of pin. Okay, so the outer diameter do is equals to 2d. It will be 134 mm as per the calculation. Okay, so here we have calculated the outer diameter of eye and fork. Okay, next is let us calculate the diameter of pin head d1. Okay, here you can see that diameter of pin head. So diameter of pin head is 1.5 times the diameter of pin. Diameter of pin is d, which is 67 mm. So as per the calculation, the diameter of pin head is 100.5 mm. So I have rounded it to the next digit of 101 mm. Okay, next is whatever the dimensions we have calculated the thickness of I, we have calculated the thickness of 4, we have calculated the inside diameter of I, that is nothing but the diameter of pin, outside diameter of I, do. Okay, so let us check for the whatever the calculated parameters or calculated dimensions of I and 4. We have to check that whether the I and 4 is safe in tension, shear and crushing. Okay, so let us check the stresses in I. So first of all, let us consider the tensile failure of I. Here you can see that after the application of force P, there is a possibility of failure of I in tension. Okay, it will fail in this along this plane. Okay, here you can see that. So we need to calculate the thickness of this area. So here the formula to calculate the area is sigma T is equals to P by A is the actual induced tensile stress, and the area will be B, that is B is the thickness of I. Here this dimension is B, so this is the thickness of I, and D is the inside diameter, DO is the outside diameter. So the area under tension will be B into DO minus D. Okay, so when you will put the value of B, DO and D in the equation and P, as per the calculation I found that the induced tensile stress is 34.98 Newton per mm square. So after the calculation, this is the actually induced shear tensile stress for the values of B, whatever the values we have calculated as per the empirical relation for the values of B, DO and D. This much amount of stress will get induced inside the cross section XX, okay, or inside the I. But the permissible stress or allowable stress for the I is 75 Newton per mm square. So you can see that the induced stress is less than the permissible stress. So our design is safe. When the induced stress, that is sigma T, it will exceed the permissible or allowable stress, then we have to go for the redesign of the component, because induced stress should not be greater than it should not be greater than the permissible or allowable stress. Next is the failure of I in shear. Okay, so here you can see that after the application of force P, there is a possibility of failure of I in shear along this plane. Okay, here you can see that there is a double shear failure. So obviously the area will be 2A. So tau is equals to P by 2A. P is the applied force, A is the cross sectional area. So here I am going to calculate the approximate area. Okay, here you can see that this is the approximate area, this is the wall thickness. Okay, this will be outer radius minus inner radius multiplied by the thickness of I. So here thickness of I is actually B. Okay, and this is the thickness. Okay, so here the formula will be tau is equals to P divided by B into DO minus D. So let us put the value of B, DO, D and P in the equation and calculate the induced shear stress. So as per the calculation, the induced shear stress is 34.98 Newton per mm square, and allowable or permissible shear stress which is provided in the numerical, it is 60 Newton per mm square. So here we the calculated induced shear stress is 34.98 and allowable stress is 60. So the calculated induced stress is less than the allowable, so our design is safe. Next is, let us check for the crushing failure of I. As we know that when the force of magnitude P will be applied on the I, the portion of pin which is contained inside the I, it is having the thickness of B and diameter D. It will get crushed inside the I, or vice versa, the inside portion of I can get crushed because of the pin. So let us calculate the crushing stress. Sigma Ck is equals to, actually in the problem the allowable or permissible crushing stress is not given in this problem. So when the allowable or permissible crushing stress is not given, we have to consider the allowable or permissible crushing stress equals to the allowable or permissible tensile stress, which is 150 Newton per mm square. So here the crushing stress sigma Ck is equals to force divided by projected area. Here projected area is the area of pin Okay, the area of pin which will be inside the eye. So the height of pin of the thickness, it will be equal to the thickness of eye and the diameter d. So b into d is the projected area. So sigma ck is equals to p divided by bd. Okay, so let us calculate sigma ck. So whatever the as per the empirical relation, we have calculated the thickness of eye b and the diameter of pin d. Okay, put the values of p, b, d. After the calculation, I found that the induced crushing stress is 34.98 Newton per mm square. Okay, and the permissible is 150 Newton per mm square. Okay, so here we can observe that the induced one is less than the permissible one. Okay, so our design is safe. Okay, because the induced crushing stress is less than the permissible crushing stress. Next is we have to check for stresses in fork. So let us check the induced tensile stress in the fork. As I have already explained, after the application of force, this area of eye of fork will be subjected to tensile stress. So here sigma t is equals to p by a. Area under tension is 2a into do minus d. So let us put the value of a, do, d and p in this equation and calculate the induced tensile stress. So as per the calculation, I found that it is 28.7 Newton per mm square. But the allowable, that is permissible stress in tension, which is given in the problem, it is 75 Newton per mm square. Once again, whatever the induced, here you can say that whatever the induced tensile stress, it is less than the permissible. So our design is safe in tension. Okay, next is, let us check the induced shear stress in fork. So here I have shown that after the application of force P, this portion of fork, it will get tear off, it will move towards this side. Okay, and this portion will move towards the right side. Okay, so this is the area. Here I have shown the area which is under shear. So this is the double shear failure. Okay, so here tau, that is induced shear stress, will be equals to p divided by a. Okay, so here area is 2a into do minus d for the double eye of 4. Okay, next is when you put the value of a, do, d and p, let us calculate the induced shear stress. So as per the calculation, it is 28.7 Newton per mm square. So this is the induced, and the allowable or permissible shear stress is 60 Newton per mm square. Once again, the induced stress is less than the permissible one. So our design is safe. Design of fork in tension is and shear is safe. Okay, so here next is, let us check the crushing stresses in fork. So here you can see that in the problem the crushing stress is not given. Once again, I am going to assume that the crushing stress is equal to tensile stress, which is 150 Newton per mm square. So here after the application of force, you can see that the portion of pin which is inside the eye, so this portion of pin and this portion of pin which will be inside this eye of 4, inside the inner diameter of 4, it will get crushed, or the inside diameter of 4 can also get crushed. Okay, so the projected area is sigma ck is equals to p divided by 2ad. Okay, so here sigma ck is equals to 150 multiplied by 10 raised to 3 divided by 2 into a is 39 and d is 67. So as per the calculation, I found that the induced crushing stress is 28.7 Newton per mm square. So here the but the permissible crushing stress is 150, which is equals to the permissible tensile stress 150 Newton per mm square. So as again the induced crushing stress is less than the permissible one, so our design is safe in crushing also. Okay, so here I have mentioned the dimensions which we have found according to the design. First we have calculated the diameter of rod D, which is 51 mm. Next we have calculated by using empirical relation enlarged diameter D1, which is 57 mm. Next we have calculated the thickness of fork, which is A, 39 mm. thickness of eye, which is B, 64 mm, diameter of pin, this is the diameter of pin, 67 mm, outside diameter of fork, that is DO, 134 mm, diameter of pin head D1, 101 mm, this is the diameter of pin head. Induced stresses in eye, sigma T 34.98, tau 34.98, crushing stress 34.98 Newton per mm square. So induced stresses in fork, in that first is the tensile stress, induced tensile stress, which is 28.7 Newton per mm square. Second is the induced shear stress tau, 28.7 Newton per mm square, and induced crushing stress sigma ck, 28.7 Newton per mm square. So after the design, we found these are the dimensions, various dimensions of knuckle design, and these are the induced stresses for which the design is safe. Okay, so do subscribe for the upcoming videos of machine design. Thank you.